Hello, John Lightson. So here we'll describe linear operators on a vector space which are central. And centrality means that they commute with everything. So if the set of all linear operators on the vector space V is denoted like that, then the center is just everything which commutes with everything else. So the condition for a linear operator to be central is the following: that for any other or any linear operator at all, the compositions are the same. So we will describe them. First remark is there are easy answers for such linear operators. Just take the identity operator on V and take its scalar multiple. So all scalar multiples, if the ground field is, say, F, we will have that many linear operators which will commute with everything. So the commutativity property for scalar operators is because scaling is transparent by linearity with any linear operators. So these both are linear, Z and T. And I'm writing the answer, but the obvious part of this answer is that any scalar operator is central. I'm going to argue that any central linear operator, any operator satisfying this, will have to be scalar. So if we are interested in operations on this endomorphism set, we have two: we have composition and we have addition, and they together distribute through each other, so we have what is called a ring, and the answer will be just the scalars, right? Because if this is true, then all our central operators are just as good as scalars. So this isomorphism is a natural one, taking identity and multiplying by the number. Okay, so now I have to solve this. And that is a system of many equations, one for each linear operator. So I'm free in choosing and constructing my linear operators and checking this equation for those and then seeing what it says. And that's what I will do. I will construct the following linear operator. I will take a vector, choose a vector, non-zero vector in the vector space V, and a non-zero linear function on the vector space V. So that will be vector from the dual vector space. And then I will construct my operator as follows. So the answer will be say denoted this way, and as an operator it will take x and it will we'll take the linear function and evaluate it on this x, and then the result is a number and we multiply it with our vector v. That is a formula, but what does it mean? Well, it means what it says, but yeah, what is this sort of special property of these operators? These operators are operators of rank 1. The image of such is just the line generated by vector v, and this is a generic form of an operator of rank 1. And now we will check the centrality condition with respect to these operators. So the if this is my t, then that composition evaluated on x will be, if I compute this value first, I will write it in a different order: scalar first and then the vector. Then using linearity of z, I can rewrite it like that. And well, I'm checking it, but the other order composition will be, well, I have to take this vector and treat it as my variable, treat it as my input, substitute it into the linear function, and then scale with this constant, my vector v. So these two have to be the same, right? This is what centrality in particular says. And what does it mean? I would say that, okay, first, what are my my freedoms in choosing v and l? They are arbitrary, and then there is a freedom in this equation. That is an equation between two operators, so it works for all vectors in v. Well, I chose my l to be non-zero as a function, so there should be some vectors which will keep it non-zero when I substitute them in. And that means that I can choose x to be such that the value of L is non-zero. There are plenty of such. So that means that this is non-zero scale, which I can cancel out, and then I will have the equation that my operator on the vector v is, I'll write two numbers as a ratio. So these are all numbers, and then times v again. So my operator scales the vector v with some coefficient. What is inevitable is this coefficient doesn't, well, we write it as a function of x, but it should not depend on x. It just depends on v. So what it says that my operator has v as its eigenvector. It scales it up with some coefficient c. And v was arbitrary, just took some, and I took some. So v is any non-zero, but yeah, even 0 will work. For any vector v, my operator z scales it with some coefficient. The coefficient might depend on v, but that's what I'm going to prove now. I'm going to call it lemma. I'm going to prove that if I have an operator such that all vectors are eigenvectors, such that for any vector I have a number, then this operator is scalar, is one of those. So these numbers, which might be a priori different for different vectors, will have to be the same. So that's what I'm going to prove. And assume that I have two vectors. So I have v and I have u in my vector space, and on both the operator scales them up. Some other coefficient perhaps. And actually the operator scales all the vectors up. So if I take the sum, then it has to be a scalar multiple, say e, of that vector which is the sum. But using linearity, I can rewrite the sum as the sum of values, and each of them is a scalar multiple of the corresponding input. And so I have this equation. Yes, now it's back to the choice. If they are proportional, well, it's automatic, then the coefficients which they scaled with have to be the same. So I can assume that these two vectors are linearly independent. And then I have an equation, so this is some coefficient e. I have this equation, and my u and my v are linearly independent, so I can rewrite this equation, say, as e minus c times u plus e minus d times v equals 0. They are linearly independent, both coefficients are 0, so what it says is that c and d are all equal to e as desired. So my operator has to scale different vectors with the same coefficient, it has to be scalar. And that's the conclusion. That's why I'm done here, because I had my operator manifestly scalar just from this commutativity property. That scaling property came out. Okay, let me draw a line and then look at a different but very related problem. So let me restrict myself to invertible operators. They form a group, general linear group, and again I will be asking myself which such invertible operators, which of them commute with everything. So that will be the same equation, but now T can be any invertible operator, not just any linear operator at all. And again, the easy solutions are scalar, but this time I have to keep only non-zero scalars, and this as a group is just the multiplicative group of the ground field. So obviously they commute with everything, but now I'm to prove that that is the only solutions for the centrality equation. The proof is very similar, but I will have to use something else rather than these rank 1 operators. Rank 1 operators are usually non-invertible unless the vector space is of dimension 1. So we have to imagine something else. And the thing I will imagine is the following. So that will be, I will call it TVL. That will be, in short, just the identity operator plus EVL. To make it invertible, I need to assume something about my pair of a vector and a linear function. I need to choose them such that the value of the linear function on the vector is 0. So that is the condition that the operator before is nilpotent of degree 2. And that is enough for the sum to be invertible, but we can just compute the inverse. So the inverse, I will write the answer in short. We just need to replace L by negative L. So as an operator, TVL on X is X plus that multiple of a fixed vector V. Its inverse, I say, is X minus Lx multiple of V. And to check that something is the inverse to something else is very easy. We just need to compose them. Well, in general, we need to compute two compositions, T following inverse and the other way around, but with matrices or with linear operators, it's enough to compute just one. But yeah, you can check that both work. So this composition on X will be computed in steps. So first I apply the inverse and I have this difference. And then I have to take this as an input and plug it in here and see what happens. So first I just keep it as it is. That's my first instance of the variable. And then L of all that as the variable inside the functional. Then I can use the linearity of the function and rewrite this difference as the difference of values, and they will be coefficients for V. And one thing to notice is that one of these values will be L on the multiple of V. And multiple or not, L of V is 0, so that will be not appearing, and what will be in my expansion is just L of X times V. But I already have negative L of X times V, so all what is left is just X. The composition is the identity, X is arbitrary, I'm not changing it, not choosing any special property for it. So that is an invertible operator, and it is a sum of identity and something which I know what it gives in sense of commutativity. So then I could say that if my invertible central element Z commutes with these operators, it is the same as if it commutes with operators which I used before, with rank 1 operators. They are non-invertible, but they are easy to deal with. Well, not much easy, but it's just the same equation if you expand it. And that equation says that this operator Z has to be scalar. So we're done. Well, it says it if we check commutativity for any pair V and L, and here we have the restriction, but you can see that this restriction doesn't affect the argument. The argument was choose some V, choose some L. Well, we can assume that L of V is 0, but then we were choosing some variable X, some vector for the variable, which doesn't annihilate our linear function. We're never in contradiction with this extra assumption, so this still implies that that is scalar. So we are almost done. The last statement I want to state is the following. Let's draw another line and then look at the center of the special linear group. Special means that we keep only operators of determinant 1. So this time the answer will be, you can say that these two answers are very, very similar, but the answer will be still similar, but looking differently. So we will still be seeing only identity operator scaled with some coefficient. This time the coefficient will have to be a root of 1. And here is the dimension of the vector space V. And as a group, that will be the group of roots of degree n in my base field F. So why is that? Well, first observation is, if I look at scalar operators, to have them inside my special linear group, I need to impose this condition, because the determinant is just the power of the scalar. And if I want it to be 1, I need to have a root of degree n. And the second observation is very straightforward. So these operators which I checked commutativity for are all inside my special linear group. Their determinants are all 1. Actually, these operators are what are called elementary matrices, or matrices of elementary transformations, if we choose a basis and compute them in this basis. And if V will be one of the basic vectors and L will be one of the dual basic vectors. So this will be elementary matrices. They will have ones on the diagonal, and somewhere outside the diagonal will be some non-zero element. Their determinants are 1. So that's it. More is to come.